Welcome to our session on the Brownell motion. For the reading material, our main reference is our textbook by Thomas Mikosch, Elementary Stochastic Calculus, and here it is paragraph 1.3. We have two more references in more detail, Stochastic Calculus and Introduction with Applications, and from a slightly different point of view, the textbook by Ross, which used to be a textbook for this course, Introduction to Probability Models, in paragraph 10. Details on the reading material you also find on the course web page, and there you can also find links if you can download the reading material. As the Brownell motion is a Gaussian process, we first revise the multivariate normal distribution. So recall that a random vector z consisting of n random variables z1 to zn is multivariately standard normally distributed, denoted as z being normally distributed with mean vector 0 and covariance matrix being the identity matrix, if the components z1 to zn are independent and identically standard normally distributed. More generally, a random vector x is consisting of random variables x1 to xn, is multivariately normally distributed with mean vector mu and covariance matrix sigma, denoted as z being normally distributed with parameters mu and sigma, if there exists an n by n matrix A, and a standard normally distributed random vector z, such that x can be obtained from z by this linear transform az plus mu, and where A times A transpose equals the covariance matrix sigma. So we can easily see that indeed x thus defined has mean vector mu, so that is linearity of the mean. We have A times E of z plus mu, and as E of z is 0, we have mu. Next, for the variance of x, we have A times the variance of z times A transpose, so that is how the covariance matrix behaves under linear transforms. We have the multiplicative factor going out as a factor in the front and as a transposed factor in the back. And as the variance of z is the identity matrix, we have A times A transpose, and that is assumed to be sigma. So if we look now at a jointly normally distributed random vector z1 to zn, and we look at the partition x consisting of the first m components and y consisting of the remaining components, and we partition the mean vector and the covariance matrix correspondingly, then we know that x and y are marginally normally distributed with the corresponding mean vector and covariance matrix. So if you look at x, this is the mean vector, and this part of the covariance matrix is the covariance matrix of x. And likewise, the conditional distribution of x given y is also normal with this mean here, which is linear in the conditioning variable y, and a constant given by this expression here, which is constant and does not depend on y. If the sigma xy equals 0, we see that we have here this term vanishing as well as this term vanishing, and we have that the conditional distribution of x given y equals the marginal distribution of x, which implies that actually x and y must be independent. So here in the normal case, we have indeed the case that from a zero covariance or a zero correlation between two random variables or random vectors, this already implies independence between the two random variables. So the normal distribution here is a special situation, special case. For any other distribution, we don't have this property. Furthermore, if we look at a linear combination of the random variables in X, Ax plus b, is normally distributed for any matrices A of rank m. So here we assume that the matrix A having m rows has full rank m, where we assume that the number of rows is smaller than the number of columns. So m is the maximum rank that A can have. So the row vectors are linearly independent, and Ax is 0 if and only if x equals 0. So we can generalize actually this situation, so where we say that any linear transform of normally distributed random vector is normally distributed if we allow for singular normal distributions on subspaces. So we call normal distribution singular if the covariance matrix is not of full rank. And then the normal distribution has actually a density which is on the subspace of the full dimensional space in which the singular lives. So we have one important property that is a direct consequence of the definition of the normal distribution, namely that linear transforms of normally distributed random vectors are again normally distributed. The transformation of the mean and the covariance matrix is clear. So the main result here is that we actually have a normal distribution. We will also need the moment generating function. So if we have a normally distributed random vector x with mean vector mu and covariance matrix sigma, then the moment generating function of x is, which is defined as the mean of e to the tx, as x is a random vector, t is also a vector, so we have here the scalar product t transpose x. And this moment generating function equals in the normal case the exponential function at mu transpose t plus a half t transpose sigma t. In the special case where x is standard normally distributed, we have that we have simply a half t transpose t. Now, a stochastic process X is called a Gaussian process if all its finite dimensional distributions are multivariately normally distributed. So that means for all natural numbers n and all time points t1 to tn, xt1 to xtn are jointly normally distributed with means mu ti, so these are parameters, and covariances, the covariance of xti and xtj equals gamma ti tj. And Gaussian process X is called stationary if for all time points t and s we have mu t not depending on t, so being constant, so the mean of the process does not depend at all on the time point, and the covariance between x at time point t and x at time point s equals actually is only dependent on the difference between the time points t minus s. So recall that this completely defines the distribution of a Gaussian process, as the distribution of a stochastic process is always completely determined by the finite dimensional distribution. That is exactly what we do here. And in the normal case, actually, we only have univariate and bivariate parameters. So as we do not have higher order dependencies between the random variables, we only can have linear dependencies. Mean and covariance are fully sufficient, and the covariance is actually just a bivariate parameter, as it only involves two random variables. Now, starting with the Brownian motion, a stochastic process B is called a Brownian motion, or also Wiener process, if it starts at time 0 with 0. Then it has stationary and independent increments. So that means that Bt minus Bs, for instance, is independent of Bs minus B0. And likewise, stationarity implies that this increment here, Bt minus Bs, as the time lag between Bt and Bs is t minus s. This has the same distribution as B at t minus s. Then Bt is normally distributed with mean 0 and variance equals to sigma squared t. So the variance increases with time, and we see immediately that a Brownian motion cannot be a stationary process. Finally, very important, we assume that a Brownian motion has continuous sample paths with probability 1. Then we can easily see that the increments Bt minus Bs are normally distributed with mean 0 and variance sigma squared t minus s. That is exactly a direct consequence that Bt minus Bs has the same distribution by stationarity as B at t minus s, and that by the third condition here is normally distributed with mean 0 and covariance variance sigma squared t minus s. Furthermore, the finite dimensional distributions of a Brownian motion are multivariate Gaussian with mean vector mu and covariances between Bt and Bs being equal to sigma squared times the minimum of t and s. So for instance, if s is smaller than t, then the covariance between Bt and Bs equals sigma square s, which equals the variance of s. So assuming that s is smaller than t, then that equals sigma square s, which is the variance of Bs. For a proof of the finite dimensional distribution, let us consider the vector of the increments. So for time points t1 to tn, we have the increments and these are jointly normally distributed with mean vector 0, and the covariance matrix is a diagonal matrix with on the diagonal sigma squared times the length of the intervals over which we take the increments. So we have here Tn minus 1, etc. sigma square T1. Now the vector of the Brown motion at time points T1 to Tn can be written as a linear transform of this vector of increments. So Btn is the sum of the increments, and Bt1 is only the first increment, Bt2 is the sum of the first two increments, etc. And because linear transforms of normally distributed random vectors are again normally distributed, we immediately have that we have a normal distribution with again mean vector 0, and the covariance matrix equals this matrix 1 times the covariance matrix of the increments times the transpose of this matrix, which then is row vector 1. So we have a lower triangular matrix of 1s and above the diagonal only 0s, and here we have an upper triangular matrix with 1s and below the diagonal 0s. And if you multiply that out, so for instance for this first element here we have to take this vector times this matrix, so each element here is multiplied by the corresponding diagonal element, and then multiplication by this vector sums all of them up. So this matrix here becomes sigma squared Tn. Then for the next element we have to take here the next row vector, so we are missing the first element, so we don't have this here, and then so on, so we gradually decrease the number of elements here summed. So we get sigma square Tn minus 1 up to sigma square T1, and in the other direction it is similar, so we have actually this structure, and here it's going down. No, this is T1, that is T1, and that is also T1. So what we see is that the covariance of Bti and Btj, assuming that I is smaller equal j, is indeed sigma square Ti. So next, if you compare now the Brownian motion with the Poisson process, so the Poisson process we met in the last exercises. Poisson process has also independent stationary increments. However, in contrast to the Brownian motion, which has almost surely continuous sample path, the Brownian motion is a pure jump process, so it is piecewise constant and always jumps by exactly 1. So both are characterized in terms of independent stationary increments. And one can actually generalize this to the so-called Levy processes. So these are all processes with independent stationary increments, and they have 3 components: a drift, a Brownian motion, and a jump component, which either is a Poisson process or a generalization with infinitely many jumps, but very small, infinitesimal small jumps then. And we can characterize the Brownian motion. So we defined it actually by the property that besides stationary and independent increments, we require also here normality and continuity of the sample path. Actually, it is the case that this normality is not needed. The stationarity and independence on increments together with the continuity of the sample path actually already implies normality. So we find that every continuous time stochastic process which has independent stationary increments and almost surely continuous sample path is actually a Brownian motion. So to look a little bit more in detail what kind of processes Brownian motions are, we know by the definition of the Brownian motion that the sample paths of a Brownian motion are continuous. That is, however, as nice as it can be for the sample paths of the Brownian motion, as they are, for instance, nowhere differentiable, and moreover, they have so-called unbounded variation on any finite interval, say, for instance, 0 to capital T. So that means that the length of the sample path is actually infinity. So that means, for instance, if you wanted to hike onto a mountain, so which is a certain distance, straight distance t away, and you would follow a Brownian motion as path to the top, then you would actually never arrive, as the path would be of infinite length. So that is due to all the little up and downs that were also explained here by the non-differentiability. Even so, we have continuity. Kind of the Brownian motion is always changing direction, is nowhere differentiable, and with all these changes of direction, we have actually unbounded variation and infinite sample path length. So heuristically, it is clear that we cannot have differentiability. So the basic function that has a non-differentiability, say at point 0, would be the absolute value. So which actually is a function where we come to 0 with one slope in one direction, and then we change direction. Now, because in the Brownian motion we have that the increments are independent. So the next increment, so here for instance we have a negative increment, as the next increment over the next very small time interval is independent of this one. It either can go down further or it can actually change direction and go up. And that is actually in each point. So heuristically, if you say every second point, which is nothing that makes sense in the continuous time, it is clear that we cannot have differentiability at any point. We will see that later. So what we find is that despite we have continuous sample paths, the sample paths are highly irregular and have an infinite length on any finite interval. Something that also highlights this property is the so-called self-similarity property. So we call a process self-similar or H self-similar for some positive constant H if its finite dimensional distributions at time points t1 to tn satisfy this relationship, so multiplied by a factor t to the h, they are distributed like the process at time points capital T times t1 to capital T times tn. So in particular, the Brownian motion is a half self-similar. So that means if we take the Brownian motion at time points t1 to tn and we multiply it by square root t, then, so for instance, say t equals 2, then, and we consider for instance the time points on the interval from 0 to 1, then multiplying the Brownian motion on this interval by square root 2, we find that if we have the same distribution as the Brownian motion of similar spread points on the interval 0, 2. Okay, so that means that the process on some interval behaves similar with some scaling on smaller or larger intervals. That means if we zoom into the process, so if we have, maybe the next slide here explains that visually. So if you have here the sample path of the Brownian motion and we zoom into the sample path, so for instance we take here the first part and we zoom in, we find again a sample path that just looks like Brownian motion over the same interval. And then if we continue to zoom in further, so here we start from 12 to 0.25, then so this stretch is here also seen, so we can, if we look in detail, for instance this peak is this peak here and this corresponds to this one, and after rescaling, so plotting it on the screen on the same length interval and adapting here the scaling correspondingly, we actually see that we cannot distinguish between the three pictures. So if they were completely mixed, we couldn't tell which one is on which zoom level. So that means the process, if we zoom into a small part, looks just as the process on the original scale again. So going back, using this self-similarity, we can easily prove the non-differentiability of the Brownian motion. So we prove it at an arbitrary and then say at the 0 point, but it holds for any point. So we look at the probability that here we have the differential quotient, that the supremum over a time interval from 0 to Tn, where Tn is a sequence that converges to 0, so we take smaller and smaller time intervals that n take to infinity. So we are here looking actually at the convergence of or non-convergence of this differential quotient. And if it does not converge, it actually should be larger than some x, or say any x actually. So we first can put the limit out. Then in the next step, rather than looking at the supremum over the whole interval, we only look at the quotient at the time point Tn. By that we get a smaller event, so a smaller probability, so we have smaller equal. And of these probabilities, as these are not necessarily strictly decreasing, here it is clear because of the supremum that as Tn decreases, the probabilities get smaller. Because of that, here we take the limit superior, so within the limiting sequence the largest value. So we have the probability that the quotient at time Tn is larger than x. And now we can use the self-similarity. So we take a factor square root Tn. So, or say more precisely, using this here, 1 over square root Tn. So we have Btn over square root Tn times square root Tn equals P times Tn over Tn, which equals 1. And that was with one of the square roots, so the other is still there. Square root Tn, so we have here 1 over square root Tn b1. So we have a standard normally distributed random variable. b1 is standard normally distributed over square root Tn. Now as Tn converges to 0, the probability that b1 is larger than square root Tn over x eventually becomes 1 as Tn decreases to 0, and in the limit we have absolute value b1 is smaller or equals 0. So that means for arbitrary x, the probability that the ratio differential quotient exceeds an arbitrary value x equals 1, so we cannot have differentiability where this should converge to some fixed value. From the Brownian motion we can derive a number of useful processes. The simplest one is the so-called Brownian motion with drift. So we simply add a linear drift mu t to the Brownian motion. So then, of course, the mean of this process becomes the linear drift mu t, while the here the additive constant does not matter for covariances. The covariance of xt xs equals the same as the covariance of pt and ps, so we have sigma squared minimum ts. And that is the picture here. We have here the trending line, and we have Brownian motions, here 5 realizations that are distributed about this line. We see that the variance increases, so while at the beginning the 5 curves are close to this line, they spread more and more about the line as the time continues. The next important process is the so-called geometric Brownian motion, where we take the Brownian motion with drift and put it into an exponential function for positive points, time points t. Then xt is log normally distributed, so if we take the log of xt, we get back the Brownian motion with drift, which is normally distributed, so we call a distribution then log normal. Using the moment generating function of the normal distribution here, we find that the mean of xt is e to the mu plus a half sigma squared in brackets times t. And the covariance, a little bit more complicated, can also be evaluated. The covariance between xt and xs is given by this longer expression. And for an illustration, we have here again 5 sample paths, and now they're starting at 1. They are distributed about this exponential curve here. So as we see, they are all positive by the property of the exponential function, which cannot take negative values, or on the real line actually only can take truly positive values. And we find also that the speed by which this process increases, so it is an exponential function. Finally, we have the standard Brownian bridge, so which starts from a point at time 0 at point 0 and ends at time 1 again at 0. So it can be formally obtained from a Brownian motion by taking the Brownian motion and subtracting t times b1. So at b1 we have b1 minus b1 equals 0. The mean of this is a linear transformation, so we have again a Gaussian process, and the mean of course is 0, and the covariance can be seen as being the minimum of the 2 time points minus the product of the 2 time points. Now for the existence of the Brownian motion, or also on the simulation of Brownian motions, a little bit of theory. So if we consider functions on the interval 0, 1, we let L2 in bracket 0, 1 be the space of all square integrable functions. Then this space here is what we call a separable Hilbert space, which is a real-valued vector space that has a scalar product and a norm. So the scalar product between 2 functions in this vector space is given by the integral of the product of the functions. And if we take in this scalar product the same function, and then the square root of the scalar product, we obtain something that we call a norm, and which measures the size of a function. This space L201 has actually a very nice property, namely that it's a separable Hilbert space, which means that it has a countable orthonormal basis. So that means if you have a function in this space, then this function can be actually represented as a infinite sum of these basis functions times some coefficients an. Okay, and these coefficients in this space actually are square summable. Okay, so for such a separable Hilbert space, such a basis exists, and we can represent every function in that space in the sense where the convergence is in the mean square sense. So that means the difference between this limiting function and the approximating finite sums here converges in mean square to 0. So the mean, which is here actually the norm of the difference converges to 0. So furthermore, orthonormal basis is orthonormal if firstly any two basis functions are orthogonal, so the scalar product of any two of them is 0. If you take the same one, that is actually the norm squared, that equals 1, so the length of a basis function here is 1. So, as already said, every function can be represented in this form, where actually here this convergence is meant in the mean square. Now we can define a Gaussian process, and that is exactly what I meant in the introduction. We can define stochastic process on general index sets, and here we take as an index set actually this function space of square integral functions on the interval 0, 1. So for each function which has this representation for some orthonormal basis phi of the space here, and a sequence of standard normally distributed random variables, independent, we obtain a normally distributed random variable gf that equals the infinite sum of the products of these random variables zi times ai. Okay. Here the same, that should be actually ai, here the same ai. Because these sums, the sequence of the a's is square summable, this gf, this sum here, converges almost truly and in mean square, so in that sense this process is defined almost truly and in mean square. So for each function f in this space, we have a normally distributed random variable. Then, using this process G, we can obtain or define a Brownell motion on the interval 0, 1 by simply setting the Brownell motion to be this Gaussian process evaluated at the indicator function on the interval 0, t. So that means that we take from the indicator function, we determine the coefficients an, and these coefficients an are given by the scalar product of the indicator function and the orthonormal basis functions. And because the scalar product is nothing else than an integral over the interval, and the indicator function simply constrains the integration from 0, 1 to the interval 0t. You can also write that as the integral from 0t of the basis function phi n. So if that explains this expression, so we have a linear combination of these independent standard normally distributed random variables with exactly these coefficients. Then the resulting process Bt is indeed a Brownian motion, so the mean of Bt is 0, the variance is exactly t, as I think that is called the Parseval's identity. The sum of the squares of these coefficients is actually the integral of the square of this indicator function, which is 1 or 0, so this is the integral of the indicator function, and that is exactly t. For s being smaller than t, we have we have that the scalar product of the indicator function from 0 to t and the indicator function from 0 to s equals the scalar product of the indicator function from 0 to s and the indicator from 0 to s, so the norm square, and that is exactly, as already said, s. So this implies that the covariance of Pt and Ps equals the variance of Ps equals s. So finally, we now want to determine a particular orthonormal basis. So there are plenty of orthonormal bases, like for instance a Fourier basis. A particular simple one is the so-called Haar basis. So where phi of x is takes the value 1 on the interval from 0.5 and the value -1 on the interval from 0.5 to 1. So that looks like this. Then we have actually also a phi 0, that could be called phi 1, which is simply 1 on the whole interval. We can already see that if we multiply those functions and integrate, we actually get here the value 0. So phi 0 times phi 1 equals phi 1, and that integrated here, as we have one positive, one negative area of equal size, we exactly have 0. Now the next orthonormal basis functions are of similar form, but they are then only on half of the interval and scaled to have norm 1. So if we square them, the absolute area under the curve equals 1. So we have exactly this here. Phi 0 equals the identity on the interval, and then we have phi n, these functions where n has this representation. So we have here one first function then we have 2 functions living on the half interval, then we have 4 functions living on quarter intervals, etc. So that is this partition here in expression in terms of powers of 2. And one can easily see that we have an orthonormal basis. And if we then take the integral of these functions, so d0 equals t times indicator, delta n equals, so that is delta, the integral of this function here from 0 to t, and with this scaling here, delta n is the correspondingly scaled integral, and then we can express the Brownian motion as an infinite sum of standard normally independent random variables times these functions delta n. So how does that look like? Our phi 0 here, delta 0, is a linear function. We multiply it by a standard normal distributed random variable. So our first standard normally distributed random variable actually will be the value of the process at time 1, which is standard normally distributed for the standard Brownian motion. And the delta 1, delta 0 is in exactly this line here. Now in the next step we add a standard normally distributed random variable times delta 1. Delta 1 is a triangle, so we have here actually added to this line a triangle, and this value here is a standard normally distributed random variable times the scaling that comes here from this function. And then the functions here become more and more. So we have here now on each half of the interval one triangle, and then we have on each quarter a triangle added. Again here in the midpoint we have for the highest point of the triangle a standard normally distributed random variable that determines this length. And so on and so on. So we get, as we increasingly add these triangles, we get a better and better approximation to the Brownian motion. So I think that is sufficient for the moment. We will discuss approximations of the Brownian motions in the exercises. So for instance, that the Brownian motion here in this representation, actually one can see that once we have added this triangle here, the point here in the middle is fixed for all subsequent steps. So like here, this step is never changed after the first step, where we have here simply drawn a standard normally distributed random variable. The second step, the process at this point is determined, and the whole process starting from here, ending here, can be seen as a Brownian bridge added to this linear line. Then once we at the midpoint of this Brownian bridge, so we have this point here, we have these two lines, and again the process here, the Brownian motion between this point and that point, can be seen as a Brownian bridge over this red line, and so on. So here as well we have a Brownian bridge from here, this point to this point, so over this line added. So that again expresses the self-similarity, that as we zoom in, we have 2 points of the process over a line, and the process between these 2 points actually behaves like a Brownian